Yeah.
The integral cutoff change to lambda to 1 minus dl in the second equation.
Very good, because I'm taking k prime and going back to k. Okay, I'm trying to find out what this really means in terms of phi of x.
Substitution or transformation.
Scaling dynamics and being
Yeah. So for those who know the answer, this is a very famous answer, b minus 2 over 2. Okay, but for those who don't know it, you're seeing it. Okay? So you have this, and then whatever's the rest of it, I claim it's just phi less of x times 1 plus dl. That's what this phi prime of x means. Okay? Good? So if you want to do everything in real space, you can. What you do is you let x go to x times 1 plus dl. Okay? And then you let the field do this. And that will keep the derivative part fixed. That's what you're saying. Okay? Good? Now, whenever you have something like this power here is known as the engineering dimension of the field. So let me write down, when I put a square bracket around this is called the naive dimension, sometimes called the engineering dimension. Okay, of the field. I don't know why it's called the engineering dimension. Maybe the physicists look down on engineers. So they think whatever's naive must be engineering. Maybe. I don't know. Okay, so that's the dimension. Alright, now let's look at the phi to the fourth term. What happens? Okay? And then we'll stop. So, let's do it in momentum space, just to be absolutely confident that we know what we're doing. Okay? So remember, the phi to the fourth term looked as follows. It had basically up to lambda times 1 minus dl. So there were 4 momentum integrations and then 1 delta function, right? So effectively 3. So let's write it as d3k1, d3k2, and d3k3. And then there was this phi tilde of k1, phi tilde of k2, k3, and finally phi tilde of minus k1, minus k2, minus k3, right? That's what my delta function is doing. Right? And of course, the condition is that all of these momenta should be less than lambda times 1 minus d. So for example, if 3 of these guys are very close to lambda and they're aligned, that's not possible. Okay? There's an extra hidden condition sitting there. It's not that important. Because for most of the phase space, these guys will add up to something small. Right? Okay, so now I do my same old, right? So I go from k to k prime. So what happens? So this becomes lambda.
So we want to change lambda by dimension?
Ah. Okay, good. Alright?
So there will be a lambda by so you are only accepting the integration.
Good. Okay? I'm so eager to get to the point. Forgetting to write alternative. Okay? Good. So you have this. Now what happens? Alright, so remember, I'm now going to do k prime, right? So it's d to the d k1 prime, d to the d k2 prime, d to the d k3 prime, right? And there's some 2 pi. Forget about that. Alright, so remember that every time I had, went from here to there was a 1 plus dl to the minus d coming, right? So there will be a 1 plus dl to the minus 3d over here. Yes? Good. And then, how about these fields here? Well, I have to do this to each of the fields, right? So I have to basically replace this. So this is what I have. I have phi tilde of k's. But I want to write in terms of phi tilde prime of k prime, right? So what will I do? I will do phi tilde prime of k1 prime, etc. Phi tilde prime of, let me call it k4 prime, which is this. Okay? But then each of these fields comes with a factor over here, right? It's the inverse of this, because I'm re-expressing this in terms of that. Okay? So it will be 1 plus dl to the power of 2 times d plus 2. Okay? So, what is the bottom line of all this? So it looks like lambda over 4. Now, how many powers of 1 plus dl are there? Well, there's 2d over here, minus 3d over there, so that's a minus d. So it really looks like 4 minus d, right? Times, basically now, I can rewrite this as d to the d x prime, phi prime of x prime to the 4th power. Right? Okay? So you can see what's going on now, right? This guy, as long as d is bigger than 4, if d is bigger than 4, this number is smaller than 1. So whatever lambda I put in will shrink if d is bigger than 4. If d is less than 4, if I put in a lambda, it will grow. Okay, so this tells you that for d less than 4, lambda is relevant. Okay?
But sir, if d is less than 4, the lambda increases.
Correct.
But
It's
the-
relevant.
Relevant.
Yeah.
But the perturbation theory requires the lambda to be small so that we can have finite number of terms.
This tells you the perturbation theory will fail. Okay? Near the critical point. You cannot do perturbation theory near the critical point. Okay, that's what this tells you. Okay? Alright. Now remember, there are all the dots. Right? So let's figure out what happens to the dots. But you guys got this, right? So as long as I'm in d less than 4, the m squared term is always relevant. Okay? This guy is relevant for d less than 4, irrelevant for d bigger than 4.
So that
Yeah.
should be x within the argument of phi prime, or because that's
It's a dummy variable of integration. It doesn't matter what it is.
so good.
Okay. I sort of went overboard in putting the price. Okay.
So for t greater than 4, this formalism will work and partition will work and this formalism will not work for t greater than 4.
No, this formalism always works. What do you mean it doesn't work? It always works. Okay? But perturbation will also work. You're a little bit careful because if you go below the critical point in d bigger than 4, you get some 1 over lambdas, right, in your order parameter. Right? So it works modulo some stuff. Okay? It's what's actually called formally a dangerously irrelevant variable. It's irrelevant, but it's dangerously irrelevant. You have to make sure in certain quantities. I'm not inventing this, by the way. This is really a phrase. Okay? All right? Fine? Now let's look at the dot. So, as part of the dot, there will be a phi to the 6th, right? So let's call it u6 phi to the 6th. Now we can do this really fast because we've got experience now, right? This guy in momentum space will have 5 independent k integrations, right? So how will it scale? So it will scale like 1 plus dl to the minus 5, correct? 5d. Okay? And now there are 6 fields which I'll have to rescale. So it will look like 1 plus dl to the 3 times d plus 2. Each of them is d plus 2 over 2. Right? So now let's count what happens here. There is 3d and minus 5d, so that's 1 plus dl to the minus 2d plus 6. Okay? So, now the question is it relevant or is it irrelevant? Alright. If d is 4, then this is minus 8 plus 6 and it shrinks. So it's irrelevant. Right? What about d equals 3, which is the word we live in, right? D equals 3, this is minus 6 and plus 6, is 0. So d equals 3 is marginal. This is a marginal coupling for d equals 3. Okay? So d equals 4, u6 is irrelevant. D equals 3, u6 is marginal. So we don't know quite what to do with u6 at the moment. So we'll figure it out as time goes on. Okay? Alright, how about u8? Try to be 8. Okay? What happens there? Well, so there will be 7 integrations, right? So 1 plus dl to the minus 7d, right? Plus 4 times d plus 2. Okay? So this one will be basically the power looks like minus 3d plus 8. Okay? Good. Of course for d equals 4, this is minus 12 plus 8, less than 0, it shrinks, it's irrelevant. And in fact, any higher power will also be irrelevant. D equals 3, minus 9 plus 8, also negative, also shrinks. So all these guys, the dot dot dot, starting from u8, u10, u12, they're all irrelevant. You can do it in general. For d equals 3. Okay? This guy is the only one that you got to worry about. You know, all those dot dot dots. That d equals 3. Okay? Of course, if you want to go to d equals 2, then there's a problem. Right? Because this guy is also relevant.